In this video, we will discuss the confidence interval for the population proportion. Remember that the sample proportion follows a normal distribution. We have seen the distribution of the sample proportion before. It requires that n is sufficiently large and p and q are not very close to 0 or 1. And the confidence interval for the proportion is actually one of the most popular ones available. And an example would be when during an election year, we will see exit polls usually that describe what is the estimated percentage of voters. So a poll for a particular candidate running for president might show that the candidate has 40% of the vote within 3 percentage points of margin of error, which means that we expect the candidate to receive between 37% and 43% of the vote. Often, election polls are calculated with 95% confidence, so the pollsters should be 95% confident that the true proportion of voters who favor the candidate will be between 37 and 43%. A lot of times, the exit polls cannot determine a winner, and that is because the error bumps either of the two candidates above 50%. So they are not sure, so they cannot determine the election. So let's refresh our memory again about the algebra behind the population proportion. With a significant sample size, we can estimate the proportion, the sample proportion variable called p prime or p hat, to follow a normal distribution with a mean of the population proportion p and a standard deviation, the square root of p times q divided by n, q being the complement of the successful completion of the question. The confidence interval for the population proportion is the point estimate minus the error, the margin of error. It's called error bound for the proportion, or EBP, comma, to the point estimate plus the margin of error. The point estimate is your sample proportion. P prime or p hat will be the notation, and you will estimate it by dividing the number of successes in the sample by the size of the sample. So how many observational units answered yes to the question that you are asking? It is a binomial experiment, so you have a success and failure divided by the number of units in the sample. As we said, EBP is the error bound for the proportion. Because this is a normal distribution, it will equal the z-score at alpha halves times the estimated standard deviation, or z at alpha halves times the square root of p hat times 1 minus p hat divided by n. And the reason we have to use p hat and not p is because in inferential statistics, we don't know the true population proportion or the true population mean, and we are trying to estimate it with the sample proportion or the sample mean, and then make some inferences for the actual value of the true population proportion. The confidence interval can only be used again if certain conditions apply that will make this a binomial experiment and a binomial distribution and eventually a normal distribution. These are that n times p hat has to be greater than 5 and also n times q hat greater than 5. And if you remember from the previous chapter, n times p hat and n times q hat greater than or equal to 10 is even better. If you are using technology, the calculator has a function called 1prop_z interval. In Art of Stat, we will use the app Inference for a Proportion. So here in the app's we will go to the one on the left, the top left, under confidence intervals and significance tests, and we will use this app called Inference for a Proportion. That will allow us to calculate a confidence interval, do a significance test in the next chapter, or find the sample size, the same that we did for the mean. And in Excel, for our project, we will use the normal dot inverse. That will require a probability in the lower tail of the normal distribution of the sample proportion, the mean and the standard deviation, the standard error for the sample proportion, and you want that probability to be alpha halves for the left tail or 1 minus alpha halves for the right tail. So let's do an example. Suppose that a market research firm is hired to estimate the percent of adults living in a large city who have cell phones. So this is actually in the population proportion. They are looking for the percent of all adults in this large city who have cell phones. And they selected 500 adults randomly, so the N was 500. And they surveyed those 500 adults to determine whether they have a cell phone. And of those 500, 421 said yes. So these are the successes, that they own cell phones. So from here we know that P hat will be 421 divided by 500, which is 0.842. And the Q hat will be 1 minus the P hat, so the rest of those people, the 79 out of 500, and that answer will be the remaining from 1, 0.158. And with this information, we want to find a 95% confidence interval to estimate the true population proportion of adult residents in the city who have cell phones. And I'm going to use the Art of Stat app. It will ask me to enter data, so I'm going to say that I have the number of successes. I'm not uploading a CSV file. I'm not uploading individual observations. I have the summaries. The sample size was 500. The number of successes was 421. The label for success is yes, or we can also call it cell phone. And the label for failure will be no cell phone. We are looking for a confidence interval that is two-sided at a 95% confidence level. And we can check the z-score. It will be 1.96 as expected. And we can see the interval here, graphed for us, and also listed in the title of this graph. So it is 0.81 to 0.874. And we can say now that we estimate with 95% confidence that between 81.0% and 87.4% of all adults in this large city have cell phones. This will be the population of adults living in this large city. So explanation of the 95% confidence level. 95% of the confidence intervals constructed in this way would actually contain the true value for the population proportion of all adult residents of the city who have cell phones. So there are 5% chances that we have not captured the true population proportion of adults that have cell phones, and we are 95% confident that we have captured in this interval the true population proportion. Here is another one. Suppose 250 randomly selected people are surveyed to determine if they own a tablet. So we are looking for the true proportion of people who own tablets, maybe in that area, maybe in the United States, depending on what population the 250 people come from. And of the 250, 98 reported that they own a tablet, and we want to have a 95% confidence interval. So I'm going to go in my app, and I will enter the sample size. Actually, we have to delete this first. I will enter the sample size of 250. The reason I had to delete the number of successes was that the number of successes was 421, which is larger than 250. So then here I will enter a 98, and we are looking for a 95% confidence level, and here is the interval 0.3315 to 0.4525. Let's look a little bit, let's explore what the app says. We have a sample size of 250, we have 98 yeses. When we divided 98 by 250, we got a sample proportion of 39.20. This also, p hat, happens to be sitting here in the middle of our confidence interval. We ended up with a z-score of 1.96. We ended up with a point estimate of p hat 0.3920. The standard error was the square root of pq divided by n. It came out to be 0.0309. When I multiplied the z-score with the standard error, I got a margin of error of approximately 6%, 0.05. And therefore, from the point estimate minus that 6% and from the point estimate plus that 6%, I ended up with the 2 bounds for the confidence interval. You can pause this video now and write a sentence to interpret the interval, use the wording that we have used before, and then restart the video to compare it to the answer that will be shown. We estimate with 95% confidence that the true population proportion of people who own tablets is between 33% and 45%. Remember that percentages do not have units because the fraction part out of the total has the same units in the numerator and the denominator that they simplify. So another way to say this statement, if you want to have things following your percentages, would be we estimate with 95% confidence that between 33.15% and 45.25% of the people, of the population in this town or in this region or whatever the population is, own tablets. You can try this one on your own, pause the video, use your technology and find your interval and interpret the interval, and then you can compare it to the example, the solution that you will see after you pause the video. Again, I used my technology to estimate with a 90% confidence level that between 56.4% and 63.6% of all students in the university will be registered voters. There is a certain amount of error introduced into the process of calculating a confidence interval for a proportion. Because we don't know the true proportion of the population, we are forced to also estimate the standard deviation or the standard error of the sample distribution. Studies have shown that the resulting estimation of the standard deviation can be flawed. Fortunately, there is a simple adjustment that allows us to produce more accurate confidence intervals. We simply pretend that we have 4 additional observations. 2 of these observations are successes and 2 are failures, and the new sample size will be n plus 4, and the new count of successes will be x plus 2. Computer science studies have demonstrated the effectiveness of this method, and it should be used when the confidence level desired is at least 90% and the sample size is at least 10. So we want 90% or larger confidence level, and we want 10 or larger sample size. So let's try to do that example. The Berkman Center for Internet and Society at Harvard recently conducted a study analyzing the privacy management habits of teen internet users in a group of 50 teens. 13 reported having more than 500 friends on Facebook. Use the +4 method to find a 90% confidence interval for the true population of teens who would report having more than 500 Facebook friends. So I will do n plus 4 and I will do x plus 2. N plus 4 will be a sample size of 54, and then x plus 2 will be 15 successes. And I'm going to calculate the confidence interval with confidence level equal to 90%. And let's try our technology. So I will have 54 and 15, and the confidence level will be a 90. So the point estimate was 15 out of 54 and not 13 out of 50. So I end up with a 0.2778 p-hat. This p-hat is right in the middle of my interval. The standard error, the margin of error came to be 0.1003. So I have the confidence interval of 0.1775 to 0.3780. And we are 90% confident that the true proportion of teens who report having more than 500 Facebook friends is between 17.75% and 37.80%. The Berkman Center study referenced above, so the same study, talked to teens in smaller focus groups but also interviewed additional teens over the phone. When the study was complete, we now had an N equal to 588, and of those 159 said that they had more than 500 friends. If we use the +4 method now to find the 90% confidence interval, our +4 will be 592 and our x plus 2 will be 161. (592) sample size with 161 successes. I end up with a p-hat that is 0.2720. This is also at the center of my interval. I now have a margin of error of only 3%, and when I subtract it and add it to p-hat, I will get the confidence interval of 0.2419 to 0.3020. And here we are 90% confident that the true population proportion of teenagers that have more than 500 Facebook friends is between 24% and 30%. Before, it was between 17.75 and 37.8. So if you noticed here, the interval became narrower. The confidence interval for the larger sample is narrower than the interval for the smaller sample. Larger samples will always yield more precise confidence intervals than smaller samples. It was also true for the population mean. The +4 method has a greater impact on the smaller sample. It shifts the point estimate from 0.26, which would have been the 13 out of 50, to 0.278, which is the 15 over 54. It has a smaller impact on the error, margin of error for the proportion when we have a larger sample, because n+4 is more impactful when n is smaller than when n is larger. In the larger sample, the point estimate undergoes a smaller shift from 0.270 to 0.272. And it is easy to see that the +4 method has the greatest impact on smaller samples.